are watching Darasa Online.
Hello, my dear student. Welcome to our physics program. It's me, Mr. Samuel John. So today we have a very interesting topic called electronics, and we shall discuss on the subtopic known as amplification and the power gain of a transistor circuit. But before we start, we're going to see what are the applications of electronics in our normal life. First, in our lives, we normally use phones, cameras, radios, TVs, and those devices, they make use of the electronics in the operations. Not only that, but we have some areas where these electronics can be applied. For example, in the security system and in the alarm system. We know that when you are dealing with this kind of electronics, there are some areas where we need to make sure that our homes and our families are protected. So we have other systems which can be used to protect. When the darkness falls, the light will be switched on. That's application of electronics. But we have this kind of display we see in the supermarkets. You see the words are displayed, welcome. This is the art of the electronics. This is where the electronics play part in our life. Now, to start with this part of electronics, today we're going to discuss about the transistor. But before we discuss about the amplification and the power gain, we're going to see what do we mean by a word transistor, and what are the types of this bipolar transistor, which are given the names BJT. These are bipolar junction transistor. What are the types? And how are these transistors operating? The mode of action of a transistor. Now, what are the configuration of the transistors? And lastly, we shall be able to find the current, voltage, and power gain of a transistor, which is the main subtopic of today. Now, let's start from the transistor itself. So the topic is the electronics. Subtopic this amplification and power gain. When you see the word transistor here, it seems to be divided into two words. Means this is the process of transferring. What are you transferring in electronics? We normally transfer signal from one region to another region. Now, this is the meaning of a trans. But Easter, we remember this is the property of devices which have a tendency of opposing the flow of current. So it's behaving as a resistor. So in other words, you can see a transistor, it's a device that transfers signal from one region, maybe of high resistance or low resistance, which I see. So it must be involving the resistance from one part, and that signal will be taken to other regions where resistance will be changing. We shall see now what do we mean by that. So by this trans and East, you can see now a transistor is defined as a devices that normally transfer electric signal from one region to another region of changing resistance, or from region of low resistance to region of high resistance. That's the meaning. But all we did in the class, we know that the transistor is normally used for amplification. 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 Amplification means the process of increasing the strength of the signal. Means increasing the strength of signal. This process is what we call amplification. Now, the device that is normally used to make use of this is given the name amplifier. Amplifier. So that's the main task of the transistor. Normally, when you see this kind of transistor, when you visit some areas like in music system, when people are making music, or in the church, we have the device which is normally used as a mixer. That's another area where the electronics can be applied. The mixer is the device used to combine different signals so that they can produce a very nice sound. So electronics is applied everywhere in the church, even those are people who are producing music. So that means here you can see what does the device normally. Sometimes it's used to combine the signals. After combining, it has to do with amplification, increasing the strength of those signals to be audible. That's the meaning of the transistor. It is used to make some amplification, and by that name is given a transistor is sometimes known as amplifier. Now we have seen the meaning of a transistor as the process, a device which transfer signal from one region to another region, as you can see from the way transistor is made. But a transistor, how do you make a transistor? There are different types of transistor, but our today's discussion we base on the bipolar type of the transistor, bipolar junction transistor, BJT. What is a bipolar junction transistor? This is a type of transistor which make use of two charge carriers. Charge carriers, bi means two. So we have two charge carriers, which are holes and free electrons. If you remember, in this part of semiconductor, we discussed how the movement of the holes and the free electrons within the semiconductor. Now, this is the type of a semiconductor which has two charge carriers. We have the positive and negative, given the holes and the free electron. Thus, we call this as bipolar transistor. It's a transistor which can be having two charge carriers within the material. But how do you make the bipolar transistor? This is made by, if you remember in your PN junction, if we dope, if a PN junction is doped with a PON, so this kind of doping, lightly doped, so you can have, if you bring a N doped with this one, so you have NPN. If you dope with the P on the other side, you can have PNP. So these are two types of the bipolar transistor, depending how you dope the type of materials with the PN junctions. So this is the PNP, and this NPN. And you can see the two types of the bipolar junctions, or bipolar transistor. Here, the majority are electrons, free electrons. Here, the majority are holes. When talk of majority means if you take here from this P arrangement of NPN, you can see we have two N. And here we have only two P. So the charge carriers, most of the charge carriers which are present here are free electrons. So that name, the name of this transistor is changing depending the number of the majority charge carriers which are present. Here we have NPN and PNP. But in most cases, we normally prefer NPN transistor because it's the one which consists of the free electrons. And free electrons, most of the free electrons are very sensitive to electrical changes, signals. We talk of they have greater mobility. It means when the small signals are applied, the signals are applied to the NPN, they respond very quickly as compared to the PNP. PNP, because the majority here has electrons, they respond slowly as compared to NPN. So we prefer using NPN transistor because it is made of free electrons which are very sensitive to any changes within a transistor. In other words, to say they have greater mobilities, they respond quickly to any changes within the transistor circuits. So we have seen types of the bipolar. Now let's see now. In talk of the symbol of the transistor, we normally use this as PNP or NPN. So can you see a transistor, either it's NPN or PNP, it has 3 terminals. So this terminal here at the end, and the other terminal at the end here. So these are terminals we have. And then you have another terminal which is in between. In between. So this is given the name the base. Base B. The base. This is given the name E, emitter. These are the emitters, and this is the collector. Collector. So a transistor is a 3 device which consists of these terminals. We have emitter, base, and the collector. And you can see from this arrangement that we did in the class, the way the transistors are made, the base of a transistor must be very thin compared to the other side of the transistor. Now, we know that that's where the charges are emitted from this side, emitter, and this is the area where charges are collected. It may be electrons or holes. Here we talk of the holes are emitted from here, and this is the area where they are attracted. This is where the electrons are emitted, attracted here. But in between, we have the junction, we have the terminal, which is used to control the amount of the charges reaching the collector. It's here. It's supposed to be very thin, because when you made this to be very wide, it means most of the charge carriers which are emitted will be combining inside, because up we have holes and here we have electrons. Most of the holes will be combining here. As a result, few holes will be reaching the collector. As a result, small current will be flowing. So the aim here is to make sure that we have small changes in one side to produce high changes in the other side. The same applied here. If you have, this is the electrons. If most of the electrons emitted here will be combined here, it means the current which will be produced here is very small. We know that when the charges flow, we have the current. So the current here is the rate of the flow of charge. It means we have N, E, T. If the number is fixed, number of charge times the electronic charge, you have this is the total charge times over time, it gives us the current. So it means if you have few charges reaching the collector, it means even the current produced will be very small. This is the reason why the base of the transistor should be very thin and lightly doped. And now, this is the diagram. But when we talk of the circuit diagram for a transistor, the circuit diagram for a transistor, if you remember, we had this. This is the type of transistor we have, and this is the arrow. Remember, we did this in a class. So we had, this is now for, if you go back to our discussion, you can see that the middle terminal here is given as the base. This is the base, B. Here, that's our base, B. And then, the other terminal. Now, we have 2 terminals here. Either, it can be the collector or the emitter. So the emitter, if you remember, the emitter is the one which must be showing the direction of the current, how the current flow. So if this is the emitter, and let's talk about that, maybe this is NPN, and this is our PNP. And you can see the way you remember in your studies, you make this life easy. You know that you can see the N is outside. So the E emitter, this is our emitter, and this is our emitter, and this is our collector. So the arrow should be pointing to where the N is. So here you can see it is the N is outside, NPN. So the arrow should be pointing outside. Here the N is in between. So that arrow should be pointing in to show that That's how the current will be flowing. So in any circuit, when we talk of a transistor, it must have the circuit diagram, which shows now base, collector, and we should know how the current flows for that transistor. If this arrow is missing, this is not a transistor. This is something else. So a transistor must have the arrow which indicates how the current flows through that transistor. So that is the how you did in your class. How do we identify the the two types of a transistor, NPN and PNP, by observing how the current flows through a circuit diagram. Okay, those are two types of a transistor we have, NPN, PNP. And I said before, we prefer using NPN because this is a transistor which most of the charge carriers are electrons, and mean majority charge carriers are electrons, and these electrons they have greater mobility, hence they respond quickly to any changes in the circuits. So we have seen types. Let's see now, how does the transistor work? Either NPN or PNP transistor work. How is a transistor work? The operation of a transistor. Let's choose N. We choose PNP. Let's choose PNP. I'm using the diagram here. This is the diagram, and we said here the base should be very thin. Now this is our 3 terminal we have. Now the principle of a transistor is that, if you remember, we said a transistor, it must have the one side where the signals are produced. It means we have the input circuit where the signal is supposed to be produced. And we have the other circuit which is responsible for amplification of those signals. So we have the input circuit and you have the output circuit. And for example here, we can see that this circuit, it consists of 2 circuits. You can make 2. So this terminal is common. This is what we call, this was the emitter, if you remember. This is our collector. This is our base. Now if you connect the voltage here across this, that will form the input circuit somewhere, and this will be our output circuit here. Now this is our base emitter circuit. This is a base collector circuit. So for a transistor to work, step number 1, the base emitter should be forward biased, and this will be reverse biased. Remember, the word of forward bias means this is P. The P, which is the P semiconductor, must be connected to the positive terminal of the power supply. Here we have the source of the power supply. This is given as VBE, maybe at voltage. And then we have this voltage here, which must be connected to this one. So that's how you can see this is positive, this is negative. So the positive terminal of the power supply is connected to the P. P means positive, and the other terminal to the negative. So on the other side, reverse, the positive terminal of the power supply should be connected to the negative, and the negative to the positive. Here, if this is P, we must have the negative terminal here, so that we can have this. This is a negative, this is a positive, and we shall see the reason why we're making this. So the voltage here, this voltage should be greater than that. We shall see the reason why are you making this voltage across the base collector to be greater than the base emitter. Now, by this arrangement, you can see, since we have these inside here, we have holes. The symbol for holes we normally use, that these holes, and we have very few electrons here. And then we have, most of these are holes. So when you connect to the power supply, this positive here, because we know it's positive and this is P, we have a repulsive. So most of the electrons, all of the holes, will be pushed across the base. So there is a movement of the holes like that. So the holes will be forced to move like that. As a result, on the other side, very few will be combining here because the base is thin. Very few will be combining here, and some of them, most of them, will be forced to across that junction, the base junction. And then, since this is negative, the negative terminal of the power supply is assisting pulling the hose which has been emitted from here. So here you can see the tendency now continues like that. This also tries to pull most of the hose across from the emitter base across the base to the other side of the circuit. So you can see most of the hose will be pulled across the collector. As a result, the current flow, remember, the hose flow will be moving in the same current. When the movement of the hose, so the current should be in the same. But when you have electrons, the current must flow in opposite. Since the electrons, if they be considered NPN, we'll be talking about the electron. But here we talk of the hose. So here we have the current produced here. This current is given the name collector current. And because we have some of the electron will be combining, some of the holes will be combining the electron here, very few will be composing a base current here. And this movement of a hose from this side will be producing what is given the name the emitter current. So we have the base current, we have the emitter current, and we have the collector current. We did this. Now let's see how the current flows. We have, if this is a very small current which has been produced here, and you can see that we want to see that the collector current will be very large. And we shall see how do we define the current gain of this kind of a transistor. Now, from Kirchhoff's law, you can see that if you consider this point as our junction, this current is coming here, and this current is coming here. These are the two coming which are going to the junctions. According to the Kirchhoff's law, according to the Kirchhoff current law, say that sum of the current entering equals the sum of the current leaving, or algebraic sum of the current at the junction equal to 0. So you can see how many currents are going to the junction here, are going to the junctions. We have I base current plus collector current. These are the current which are going to the junction. And then this current is leaving the junction equals to IE. So in any kind of a transistor you draw, either NPN or PNP, so the current relation of the transistor is given by IE equals to IB plus IC. This is the basic question you should know. When you're finding some of the parameters, that's the equation that you may be using to find either base current, collector, emitter current, depending the nature of the question. So when you talk of the operation of a transistor, the current flows, since this is forward biased and this is reverse biased, the movement of the holes and the electrons will be moving around the circuit. This circuit can have the current as shown here. So the movement of electrons and holes, these are the ones which determine the flow of the current within the circuit. So that's how the transistor works, either NPN or PNP. The principle is the same. If you have NPN, they're supposed to consider the principle number one, that the base emitter should be forward biased and the collector should be reverse biased. Okay, that's how the transistor works. Now let's see what are the types of connection of a transistor. How do you connect a transistor? A transistor can be connected in three ways, configurations. So you have three types of connecting a transistor. We are given the name, these are given the name configuration. So the first mode is given the name common base, CB. We can connect a transistor such that, so the terminal which is on the ground is given the name as the one which is common to both circuits. You have seen from this circuit that we have the input circuit and we have the output circuit. And the terminal which is dividing both, we have the terminal which is common to both input and output circuit. That is given as the common terminal. That common terminal is the one which determines the nature of the transistor we have. For example, when you have common base, So the base is common to both. So you have this arrangement here. This is our base here. This is our emitter. This is our collector. Remember, we said the arrow, the terminal which must be arrowed is the emitter. And this is the Npn transistor. So you can see here, since the base terminal is on the ground, so this kind of connection of a transistor is given the name the Npn. Or you can use the other terminal here. This is a PNP transistor, PNP, and this is our base, this is our collector, this is our emitter, and the arrow should be pointing in. So this is the first way of connecting a transistor. We shall see now, when you connect a transistor like this, you can define the current gain and the power gain. We shall see which mode is normally preferred when you are talking about the transistor. So this is given as the common base type of connection of a transistor, where the base is connected to the ground. The second mode is the common emitter. Common emitter, CE. Common emitter. We normally draw. So this time the emitter is supposed to be on the ground. This is our collector. This is our base. This is our emitter. So depending now whether you have a NPN or you have that, so this is our. You see now these two, collector, base, emitter. Let's talk about the NPN. This arrow should be pointing outside. PNP, that arrow should be pointing in. So you are comfortable now to know when you see from any circuit you are given, you should know, you should be able to identify the type of the connection of a transistor. You can have the common base, you can have the common emitter. The terminal here, which is on the ground, is the emitter. And this type now you can see is the NPN transistor, and this is the PNP transistor, if you remember. Now this is the second type of a transistor which can be connected in this way. And you can see we have different ways, but we normally have this kind of connection. From there you can choose one which produces the high current and the voltage power gain. So the third one is the common collector. CC. Same arrangement. This time now you're supposed to have a base, our emitter now here, this collector. And here we have that, so you can talk of NPN or PNP. E, C, B. NPN, this is PNP. So those are three types of connecting a transistor. We call them as configurations. We have three ways of connecting a transistor, either in common base, common emitter, or in common collector. Now let's see, how do you find the current gain, voltage and power gain for this type of transistor? And of course, if you remember in your classes, we talked about the arrangement of the two, common emitter and the common base. Because we saw that we normally use the common emitter because it has the current, it produces a higher voltage gain and a power gain as compared to the common base. But there are some areas where these common collectors are supposed to be applied. Let's see now how do formulas for finding the current gain, voltage and power gain, starting with the common collector, so common base. Common base, let's draw here. This is our, let's use the PNP. This is our PNP. And we know this is the circuit which you give us the name as the input, where the input is applied here. And of course we have some voltage is supposed to be applied here. So this is the resistor as input resistor, which is connected here. And this is our base current. Here we have the emitter current. And then we have the collector current. And here we have the resistor. That's where the output can be collected. Of course, let's assume we have this now. So this is the arrangement. We have the input resistance. This is the output given the load resistor, which load resistance as the output. And this is our input circuit. This is our output circuit. Of course, you have to consider forward bias connection. And from here, you can see on top of current gain for this kind of arrangement. So the current gain is given alpha equals to the output current, which is now IC of our input, which is IE. Then this is how you can find the current gain. So the output current over the input. So we say this is the input circuit, the output circuit. Our input current here is the emitter, and the output is the collector. So from there you can talk of now the voltage gain equals to the output voltage over input voltage. So on top of output here, we talk of the current here times resistance there over of the current here. This is IE times resistance is R here. So this gives us IC over IC over IE bracket times RL over RI. And remember, from question number 1, this is alpha, current gain, RL over, this is for the voltage gain, question number 2. Of course, you remember this formula you did in your class, so this is how you can find the voltage gain. Power, the power gain is given the output power over input power. So from there to go I, current, is the current of change of current, which is IC times the, so that is the voltage across that voltage. And then the input, we have IE times the input voltage. So you can see this is IC over IE bracket times VO over VI. If you simplify, you have the power gain of a transistor is given, this is the current gain, which is given as alpha, times our voltage gain, this ratio. This is given as the output voltage, which is giving as alpha RL over this. If you remember, we said the voltage gain equals to output over input voltage, which means it is IC over here, there. So from there, you can have that power gain equals to I squared, current gain squared, RL over RI. So depending the nature of a transistor you have, either talk of the common base or common emitter. So you can be able to find the expression for the current gain, voltage gain, and the power gain. But our today's discussion, we base on the common emitter. So the common emitter, let's talk of the common emitter, the current gain. So you can have the circuit for the current gain for the transistor of this type. And let me use the Npn transistor. This is our input here. This is our input resistance here. This is our input voltage applied here. And then of course, under normal application of the bias voltage here, we can have, this is our load resistance here applied. Sometimes we have, this is, okay, this is positive here, voltage. So this is our IC, this is our IB, this is our IE, drops there. Of course, we know this voltage here, remember, this is the voltage we call voltage across the base emitter junction. And this voltage here is what we talk about the voltage is VCE. And this is the base, this is the collector, this is the emitter. So that is the voltage which is given the name voltage across the collector emitter junction. This is the voltage across the base emitter junction. So from there, if you know the current IC, which is given as the output, and this is our base current as the input, and this is our input voltage. So you can find the current gain. Current gain, beta, here is given by, if you remember, is the IC over IB. And then from here you can have the voltage gain. Again, you have the output voltage, which is IC times this resistance, RL, over our input voltage is given by IB, base current times the input resistance. So if you make arrangement, you have IC over IB bracket RL over RI. Arrangement give us that this will be the current gain, beta, times RL over RI. So the voltage gain is given by the current gain times the ratio of the load resistance to the input resistance. Take this as number 2. You can find the power gain as the output power. So of course we talk of the current, which is IC, times the voltage. On that side is the voltage, output voltage, over input current is the base current, times the voltage, which is given his input voltage. This gives us the output power over input power, and we make arrangement to have IB over V naught VI. This gives us current gain. This gives us the power, the voltage gain, which means we can have beta, if you open the bracket, beta squared RL over RI. So the arrangement, either common emitter or common base, the formula for current gain remain the same. We should know which one is the input and which one is the output voltage, and the input and output current respectively. So we can have this is the current gain, voltage gain, and the power gain. Okay, let's see now example number 1. The question says, an Npn transistor, if you go back to, just refer what we discussed about this. Just if you don't remember, just draw this kind of transistor, Npn, and then see, it's easy now to recall back here. This is emitter, this is our base, this is our collector, okay? And it means that how many 10 power 10 electrons enters the emitter here. Of course, we remember this kind of connection. How many electrons will be entering here depending the connection of the power supply. I will remember forward bars, reverse bars. So we have the number of electrons entering the emitter here is given as 10 power 10. In what? In 10 power 6 seconds. And out of this now, if 10% of these electrons are lost in the base, what do we get from this information? 10% of electrons entering the emitter. So from here you know that current equals to what? To charge over time. Charge. Because the number of charges is not changing, the Q dt, but it's Q over time. And how to get the charges? We took N times E. This gives us the charge. So here you can talk of the current. Because we have electrons which are entering the emitter, you can have the current produced in the emitter because of that. So here you can get the emitter current, because the emitter current are produced by the flow of electrons. So here we have how many? 10 power 10 times, this is a electronic charge 1.6 times 10 power negative 19 divided by time 10 power negative 6. This will give us the emitter current. Very interesting. So it means we must be given a equation which is not direct. You should know by this statement. When the electron enters in 6 seconds, it means here you can find the current. And if you make simplification here, this will be 1.6 times 10. This will be -9. And this will be power 6. So this will be given as 1.6 times 10 to -3. So the emitter current here is 1.6 milliampere. So you're told to find the emitter current. Very simple. You get that values from the information given. In part B, you are looking for the value of the base and the collector current. So from the information given, we can see that 10% of electrons which are emitted from the base, from the emitter, they are lost in the base. So it means 10% of these electrons are used to produce the current in the base. If you remember, most of the electrons which are emitted here are supposed to reach the collector, but most of them are combined here. So these are the one which is lost, and these are the one which produce the current here. So the base current is given by how? 10% of these electrons which are produced here of the electrons which are lost from the emitter. 10% of electrons emitted from the emitter, these are the one which will be producing the base current. Why? Because these are the one which are combined here to produce the current in the base. So here we have base current equals to 100 times the emitter current, which is 1.6 milliampere. If you manipulate there, you have, this is 0.1 times 1.6 times 10 -3. So the base current here is equals to 1.6 times 10 4 ampere. So we know the base current is 1.6 times 10 4. You can find the collector current. How do you get the collector current? How do you find IC? Simple. We call back the formula which connects the, we don't have the other information, but you know that IE equals to IB plus the collector current. This is the basic question that we derived from the first time, from the beginning of the lesson. If you know the emitter current, our emitter current, which is 1.6 times 10 3 ampere, and our base is 1.6 times 10 4 ampere, you can find the collector current as IE minus IB. This is giving us 1.6 times 10 3 minus 1.6 times 10 4. Using a calculator, you can find the value of collector current. For example, if you use I'm using mine here, 1.6 e power -3 minus 1.6 e power -4 is giving us 1.4. This equals to 1.44 times 10 -3 ampere, which is 1.44 milliampere. And you compare, this IC is 1.4 and the IB was 1.6. You can see, you find the ratio. You can find that is what we call the current gain. Part B now you can take as part of the exercise. It's the same question, that we have the same arrangement, but we are told that the collector current is given as 10 milliampere. If 90% of electrons are able to reach the collector, what is the base current? Very interesting. Let's do together. We are given that in the same arrangement of the Npn transistor, we are told that the collector current, IC, is 10 milliampere, -3 ampere. In other words, it's 1 -2 ampere. That's the collector current. 90% of electrons which are emitted. So if you remember from the Npn, it means this arrangement. This emitter, collector, base. 90% of electrons which are emitted from this emitter are able to reach the collector. So it means that the collector current, it is contributed by 90% of the electron emitted from the emitter. That's the information we have. So from there, we are looking for the base current. So we know that IC equals to 90 over 100 IE. Question number 1. Even here you can make arrangements. You can find what is IE. IE equals to 100 over 90 IC. That is number 1, I think. Because we are looking for IC is given, so you can find what is from number 1. You can find IE equals to 100 over 90 times 1 times 10 negative 2.
You are watching Darasa Online.
So using a calculator, you can find that 90, which is 100 over 90 is 10 over 9, 10 divided by 9 times 10 is giving us 11. This is giving us 11 milliampere. Of course, you base this is as 10 milliampere. So it's 11 milliampere. That's IE. But the question is asking to find the base current. So from the equation that we know, IE equals to I base current plus the collector current. You can find from that equation, since we know now we know the emitter, you can find the base. So the base current equals to IE minus IC. What is IE is 11 milliampere. 11 milliampere. What is our base collector current is 10 milliampere. So you find that this is our base current, which is 1 milliampere. So the base current equals to 1 milliampere. These were very easy examples or the question, but you should know how to start in terms of the number of electrons emitted from there. Okay, now this is the question number 1. Let's see example number 2. Very quick, number 2. Number 2 says a transistor was operated in a common emitter configuration. Okay, so a common emitter, you draw the circuit. Number 2, very important, you draw the circuit here. This circuit here is in the common emitter, and it is operated in the common emitter. We can use maybe Npn Transistor, such that we know we have the input resistance, which is given here, and the input voltage is given here, and you have the collector resistance here, RL, and you have the voltage across this, supply voltage across that. This is the collector, this is the base, this is the emitter. This current here is IB, this is IC. You should have a rough diagram which shows now the information. So we have given that the VCE, so the VCE here, VCE equals to 0.6 volts. When the base current changes from this, so the changes in base current equals to how much? You take 200 minus 50 raised to 10 negative 6 ampere. This is the changes in the base, produces the change in the collector. So the collector current changes from 5 to 17. So it's 17 minus 5 milliampere times 10 negative 3. So, and you're given that the input resistance, this input resistance, Ri equals to 100 ohms, and the load resistance, which sometimes we take as the output resistance, is given as 5,000 ohms. Now, what's the question about? The question is asking what? Let's see the question. What does the question says? So the current gain equals the change in the base current over, from the collector current over the change in the base current. So you're supposed to find the difference here. This difference is giving us 150. So this difference is giving us 12. The collector change, which is times 10 negative 3. And this difference is giving us 150 times 10 negative 6. So this is the current change in the output, which is negative 3. And the base change, which of the current, the base change in the base current is given by 200 minus 50 is 150 times 10 power 6. Using your calculator, you can find how much is the current gain. Quickly, you can find that we take 12 divided by 150 and then multiply by e upon 3 power 3. This is giving us 80. So the current gain of a transistor is 80. Part A. Part B. What is the voltage gain? Voltage, remember the formula says the voltage is current gain times the ratio of the output resistance over input resistance. Because those formulas, the formulas you derived, you should remember them. So the current gain is given as 80 here, and the input resistance was given as 5,000. So the output resistance, and our input is 100. So these two zeros we cancel, and we get, this will be 40, and we have 3 zeros. This is the voltage gain. 2 zeros we cancel out, and then you have 40, and then you add 2 zeros. It's for 40,000. So that is how you can find the voltage gain. Power gain is given by the formula is beta squared RL over RI. So you take that value squared, which means 80 squared. 80 squared, or in other words, it is a current gain times the voltage gain. Very simple. Current gain times voltage gain. So here is 80 times our voltage gain, 4,000. 80 times 4,000. You get that 320,000. This is the power gain. You can use the same principle, beta squared, current gain squared times the ratio of Li over LL resistance of in the output over the input resistance. Get a value which is 320,000 as the power gain. And this marks the end of our first part of electronics. So stay tuned for the second part of this topic, which will be coming live here. Goodbye.